Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 7-1, all about wave-particle duality. So this is our first lecture in our quantum, atomic, and nuclear physics unit of AP Physics 2. We're going to be talking about photons and the main evidence for light as a photon, as a model of light, and going through the photoelectric effect and the famous double slit experiment. So what is a photon? Okay, now a photon is another model of light, okay, and it is the particle model, okay, particle model of light. And we do use it when we are interacting with light and quantum objects. So when we are talking about a photon as a particle, we can calculate its energy using the equation E equals hf, where E is your energy and h is Planck's constant. Now, Planck's constant was figured out by a famous scientist, Planck, and it is equal to 6.63 times 10 to the negative 34 joule seconds, or joules per, joules. And we will also typically use it in electron volts, which is equal to 4.14 times 10 to the negative 15 electron volt seconds. Okay. Oh, and F is, of course, the frequency in hertz. Now, another common version of this equation that we use super often, because wavelength equals frequency, or speed divided by frequency, frequency then is V over the wavelength. And if we're talking about a photon, V equals C. So another common form of this equation is E equals hc over wavelength. And this is so common that hc is also on your equation sheet. So I want to go ahead and add that here. hc. So light times that speed is equal to 1.99 times 10 to the negative 25th joules per meter. And then for using that form of the equation, they actually do it in electron volts and nanometers, since when we're talking about the wavelengths of light, we're typically on the order of nanometers. And that is 1.24, well, visible light, times 10 to the third electron volt nanometers. Visible light is on the order of 500 to 700 nanometers. 700 and 900. 700 and 900, I believe. My blue here, my blue here is 400 nanometers, and my red is 532. So it is probably 400 to 700-ish for visible light. Now, what an electron volt actually is the amount of energy gained or lost by an electron when it goes through a potential difference, or a delta V, of 1 volt. So the conversion then is pretty straightforward, because the energy Q times 1 volt, if that is just a 1, that means that 1 electron volt is just equal to the charge on an electron, 1.60 times 10 to the negative 19 joules. And that is on your conversion sheet. Okay. So what types of light have the highest energy photons? That's going to be gamma rays. They have the highest frequency, highest energy, and the shortest wavelengths. If we were talking about color, it would be violet. They are the highest energy photons, where the lowest energy is radio waves. Okay. Or if you're looking just invisible light, it would be the red wavelengths. Okay, cool. Okay, cool. So, why is light quantized? Okay, why is light always going to have some energy that is a multiple of Planck's constant? Why can't it just be any energy in between? Well, one of the main pieces of evidence for light as a particle and quantized comes from the photoelectric effect. Okay, so let me show you guys how this generally works. Okay, so in the photoelectric effect, we have two metal plates and a voltage source between them. Now, if I shine light on one of these metal plates, it can cause it to emit electrons. Okay, so we see that emitting electrons. Now, what they figured out was that the energy of the emitted electrons, okay, that graph is right here, is only related to the frequency of the light. So if I up this frequency here, okay, we can see how that energy goes up. We can see those electrons moving faster, okay, when I up the frequency. Now, this didn't make sense to scientists because, well, if light is a wave, then it should be affected by both its amplitude or its intensity and its wavelength or frequency. But what we saw is that no matter how intense the light is, for example, in this case, for sodium, okay, no matter how intense the light is, it's not going to cause it to emit electrons, okay? Where even if I have a high energy one, but at a low intensity, it is still going to cause electrons to be emitted. Not as many electrons, but it doesn't affect the energy of those emitted electrons, okay? Doesn't affect the energy. Now, since the electrons being emitted, we call those the photoelectrons, okay, right over there. Since those were only affected by the intensity, the energy of the photoelectrons was only affected by the frequency of the incoming light, not its intensity or amplitude. Okay? Now, the wave-only theory of light would predict that it doesn't matter. You could just up that energy, up that amplitude. If we shown lots and lots of high amplitude, it would have the same energy and thus same effect as a lower frequency light. But that just doesn't happen. Okay, the energy of those electrons was only affected by the frequency of the light, not the amplitude. So that got rid of our wave model. Our equations for the energy of a wave didn't match how light was behaving. So light is quantized. Okay. So let's kind of make sense of how this works. Okay, blue light with a wavelength of 443 nanometers. Okay, so wavelength of 443 nanometers is incident on a potassium surface and electrons are emitted. A current is measured until a 0.5 volt stopping potential is applied. What does this tell you about potassium? Okay, stopping potential. Let me explain what that means. So here we go. We see that I am shining intense UV light on this plate, and it is causing electrons to be emitted, measuring a current of about 0.4. So if I wanted to stop these electrons, I could apply a voltage, okay, that would repel those electrons. And you can see it happening here. There we go. And the electrons are just barely not reaching that plate. I have no more current flowing. That is the stopping potential, that minimum voltage. So let's reason this out. Okay, we have blue light with a wavelength being emitted on a potassium surface. Okay, actually, I'll do the surface down here. Okay, so we have that blue light coming in. Now, it has a wavelength of 443, so we can find its energy. We're going to use that equation. E equals HF, but we have the wavelength, so we'll do E equals HC over lambda. So plugging in the numbers that we have, HC in terms of wavelength is 1.24. 1.24 times 10 to the third electron volts per nanometer, or nanometers, divided by 443 nanometers, tells us that the energy of this incoming wave is 2.799, so 2.8 electron volts. Okay, and it's shining on that potassium surface. A current is measured until the 0.5 volt stopping potential is applied. So when this light is shined onto this surface, electrons are emitted until 0.5 volts. So that means those electrons had that 0.5 electron volts of energy. Okay, electron volts is just the volts that's needed to control stop that one electron. So they have 0.5 electron volts of energy. What this tells us is that it takes 2.3 electron volts to ionize. Okay, ionize means removes an electron, to remove an electron from potassium. Okay, because we've shown that 2.3, the leftover energy that electron had as it was traveling was 0.5 electron volts. Okay, and again, that's just because that 0.5 volt stopping potential, okay, in electron volts, that means 0.5 volts per electron. Yep. U equals Q times delta V. Delta V is 0.5 volts. Q of an electron is 1 electron volt, so 0.5 electron volts of energy. It needed 2.3 to cause it to be removed, and that is called the work function. Okay, the work function of the metal. So this is one of the equations on your equation sheet. It reads that K max, the energy of the maximum energy of those electrons, because as you saw in that simulation, they all had different speeds, equals HF minus phi. Is that phi? Phi? Yeah, phi, whichever. Where K is the kinetic energy of the emitted electrons. Okay, HF, that is the energy of the incident photon. And this is the work function. So if we're looking at this in the context of our potassium example, okay, the 0.5 was that max energy of the emitted electrons. The incoming light had that 2.8 electron volts, and the work function was 2.3. Okay, so that's how that kind of works out. Basically, it's just a conservation of energy problem. Okay, Now, the threshold frequency is that minimum frequency of light, okay? The lowest energy light that would cause electrons to be emitted. Okay, now since it is that lowest energy light, that means you're not going to have no leftover energy. So to calculate the threshold frequency, we set K max equal to 0. So then HF will equal the work function, okay? Because you subtract them, you get 0. So moving that over, HF will equal that work function. And so the threshold frequency, you can always find from that energy needed to remove the light divided by Planck's constant. Okay, cool. Okay, cool. So let's go ahead and do an example problem here. The work function for aluminum is 4.08 electron volts. So what is that threshold frequency needed to produce photoelectrons from aluminum? Well, we need just enough energy to overcome the work function. So we say 4.08 electron volts equals the energy of that light, HF. So for H, we can plug in the Planck's constant, which is Planck's constant in electron volts, 4.14 times 10 to the negative 15. So we got 4.08 electron volts divided by 4.14 times 10 to the negative 15 electron volts second, which gives us 9.86 times 10 to the positive 14 hertz. Okay. So if we looked at an electromagnetic spectrum, you would actually have to look at one of those tables. You can look back at lecture 6.1 or just Google it. But 10 to the negative 14 puts this in the ultraviolet range. So that is why your aluminum doesn't produce electricity when it's just chilling in light. But if you put your aluminum foil in the microwave, those microwaves definitely have enough energy to emit electrons, and that's what we see. Okay. So if the light of frequency 4 times 10 to the 14th is used to illuminate a piece of aluminum, what will be that K max? So we can just plug it into our equation. K max equals HF minus the work function. So we have, did we already find HF, the energy of that light? Oh, no, that's a different frequency of light. So we have Planck's constant. I'm in hertz. I'm going to need speed later, which is meters per second, more closely related to joules. I don't know the electron volts, so I'm just going to solve this out in joules for this problem and use 6.63 times 10 to the negative 34 joule seconds times 4 times 10 to the 15 hertz or per seconds. Okay, minus the work function, which I will need to convert that one since I'm converting it in joules here. So 4.08 electron volts times 1 electron volt is 1.60 times 10 to the negative 19 joules. So when I plug that all into my calculator and calculate it out, I get 6.63 times 10 to the negative 34 times 4 times 10 to the 15th. That gives us 2.65 times 10 to the negative 18 minus 4.08 times 1.6 times 10 to the negative 19. And we get 1.99 times 10 to the negative 19. 1.999, so I'm just going to go with 2. 2.0 times 10 to the negative 18 joules. which if you solved this out in electron volts, I believe it is 12.5 electron volts. Let me check. Divide this by 1.6 times 10 to the negative 19. 12.5 electron volts. So the maximum speed of those electrons, well, if we know their energy, we know kinetic energy is, keep my colors constant here, we know kinetic energy is 1/2 mv squared. So if we're solving for that velocity, times both sides by 2, so we have 2 times the kinetic energy divided by the mass, and then take the square root of it. So plugging in our numbers there, velocity equals the square root of 2 times that kinetic energy divided by the mass. Okay, this is a photoelectron, so it's the mass of an electron, which is 9.11 times 10 to the negative 11. Or sorry, times 10 to the negative 31 kilograms. And you plug that into your calculator, and you get 2.1 times 10 to the 6th meters per second. Okay, cool. Okay, cool. So another work function problem. Go ahead and try this one on your own. You should get a frequency of 1.14 times 10 to the 15 hertz. And again, this is just doing E equals HF using that work function. You have to have enough energy to overcome that work function. Okay, cool. Okay, cool. Now, let's talk about the famous double slit experiment. Now, I highly recommend that you go check out the Dr. Quantum video on this. It's excellent, does a great overview of the experiment. But I will try to explain it briefly here. Okay, so this was first done by Thomas Young in 1801. This proved that light was a wave, okay, when we did it with light. And then in the 1960s, we were able to do it with electrons and show that electrons had wave behavior. And we have continued to do these types of experiments with more and more massive particles, up to balls of like 60 carbon atoms and molecules of up to 800 atoms. But this is the basic summary. Okay? If we shine particles at a small slit, we should get 2 spots in the background. Okay, I'm going to call this particle behavior. Okay? Where if we shine a wave, a light wave, at the 2 slits, then we get an interference pattern. Now, particles don't have interference pattern, waves do. Now, what happened was when we shone electrons at this double slit, we got an interference pattern like waves. And so scientists were like, WTF, okay? Something must be going on. Maybe they're bumping into each other and they're just getting into each other's way, and that's what's causing the pattern. So let's shoot them one at a time. And so they shot them one at a time through this double slit. And again, they saw the interference pattern and they were like, okay, well, this is confusing. So what they did was they added a detector at one of the slits, okay? Little electric field detector. They could sense the changes in that electric field. And then the particles were like, oh, there's a detector there? You're fine, I'm a particle. Okay, fine, I'll be a particle. Now, what that means mathematically is that when the electrons, okay, go through the slit, okay, they are particles. Electrons and everything tested have wave behavior. So the actual reasoning and how this is justified is that once the electron goes through the slit, the electron exists as a wave of probability. Electron is a probability. Okay, that probability is captured by something called the wave function. And we will definitely be getting more into wave functions as we continue to talk when we get to the models of the electron and when we added that. But the electron is a probability or a wave function, and that wave function is collapsed by the measurement. So when you place a measurement at one of those slits, it collapses the wave function and goes back to particle behavior. But if we are not observing it, if we're just letting it go through, the electron is a probability and shows the wave behavior. Okay, and I know that is super counterintuitive, okay? But the reason that is because in order to measure something, okay, that act of measurement at that slit, we have to interact with the particle. Okay, there's no measurement device that exists that doesn't interact with that particle in some way, either through the photons that it reflects and absorbs and is emitting, or by the electric fields and how it changes and interacts with a field that's there. In order to observe it, we have to measure it, and measuring it collapses the wave function and makes it go back to behaving like a particle, even though if we're not measuring it, it will behave like a wave. Yay, quantum! Okay, cool. Okay, cool. So what is blackbody radiation? Okay, let's go ahead and look at a simulation. This is a PhET simulation. So here we can see a graph of the power density and the wavelength of light. They have the visible spectrum marked for us, so we can give that kind of in context for a different blackbody. Okay, now what a blackbody is an object that gives off light. Okay, let's stick to that for a second. Let's observe some stuff about this. We'll go up really high and we can see that wavelength. Okay, that max wavelength heading into the ultraviolet range. Okay, our sun, we can see its max wavelength right in the visible range. You think that might be why our eyes can see certain things? Okay, we can see a light bulb. Still gives off light in the visible range, but it also gives off a lot of infrared light. Okay, this is probably an old light bulb, not an LED light bulb. And then, of course, we can go all the way down to the temperature of the Earth. And we know that the Earth doesn't give off that much energy, but we can see that little bit there, that little infrared radiation that's given off by things that have temperatures, you know, like us. Wait, so are we considered a blackbody because we give off infrared radiation? Well, not quite. So a blackbody is a theoretical idealized object, one that absorbs all electromagnetic waves that hit it and emits electromagnetic waves based solely on its temperature. Now, while this is an idealized object, we use it a lot to talk about things like stars and planets and how we analyze those. So you can see that graph similar to the one we were looking at in the simulation right here, where we get that peak and that blue dot shows that wavelength maximum. So as you can see on these temperatures, as the temperature increases, okay, as we go closer to this 500,000 K, the maximum wavelength gets shorter. Okay, so it decreases, meaning that that max light has more energy. And you guys might know this intuitively. If you saw a piece of metal that was glowing blue, okay, versus a piece of metal that was glowing red, which one would you think is hotter? If you see a white light compared to a red light, which one would you think is hotter? Okay, we tend to think of the blue and that white going more towards that hot, but we know that red is also very hot because you have to get something pretty hot to have it give off that max energy in the red wavelength. Now, this has been studied and we've come up with two equations that can describe this blackbody radiation. The first one we're going to talk about is Wien's law. Now, these are both on your are on your reference sheet in the modern physics. Okay, Wayne's law is this one right here, and then we'll be talking about the one right under that as well. So we have the max wavelength, not the decay constant, that's coming later, but the max wavelength equals B, a constant, divided by T, the absolute temperature. Okay, so go ahead and add that in. The max wavelength equals B, a constant, divided by T, which is absolute temperature. So that means it has to be in Kelvin. Okay. Now, Wayne's constant, that B, is given to you on that front part of the equation, of your equation sheet, and it's equal to 2.9 times 10 to the negative 3 meters per Kelvin. Meaning when we get our max wavelength, it will be in units of meters. Okay. So we can see that relationship pretty simply there. It's an inverse relationship. Higher the temperature in Kelvin, okay, shorter the wavelength. Now, this is also related to the intensity or the power given off by this blackbody. Okay, now power we know is in units of watts, which is that energy per time. So the power given off by it is equal to A, that's surface area, because obviously if a blackbody is emitting radiation, the more surface it has, the faster it can emit that radiation. And then we have theta, which is another constant, and the temperature to the fourth power. Okay, so power equals A theta times that temperature to the fourth power. Okay, where this theta is the Stefan-Boltzmann constant, also on your equation sheet. So you can see based on that constant, we're going to need the area in meters and the temperature in Kelvin. Okay. And then just a little reminder in case you guys forget, to get the Kelvin temperature, it's the degrees Celsius plus 273. Okay. So that's how we get the power and the wavelength max given off of it. Okay. The derivation comes from like the energy of a wave proportional to power and the internal energy. Not quite necessary for this class. But what is necessary for this class is the ultraviolet catastrophe. Why does blackbody radiation, why is that a thing? Why are we learning about right now? Well, see this graph right here and see how it goes down in the ultraviolet range? We also see that in the simulation even at the very top. I can zoom on out so we can see it. But no matter how hot we get this dip of the ultraviolet radiation. Now, in a wave model of light and of these black bodies, we would expect an exponential increase of energy as we got hotter and hotter and hotter. But that's not what we see. We always see this dip, okay? And that dip was called the ultraviolet catastrophe because the math just didn't explain it right. The math wasn't math and it was wrong. So Max Planck was able to quantize light and prove that with a quantized model of light, the blackbody equations were all accurate and were able to accurately predict those spectra. So the quantization of light, further supporting wave-particle duality, was also proven. So let's just do a simple problem just to get a little bit of practice real quick. Our sun has a surface temperatures of 58,000 Kelvin. What is the peak wavelength of light given off? Well, it's already in Kelvin, so this makes that a really easy equation. We just have B over T, where B is 2.90 times 10 to the negative 3 meters per Kelvin, and the surface temperature of the sun is 58,000 Kelvin. So we plug that into our calculator. 2.9 times 10 to the negative 3 divided by 5,800. Did I say 58,000 earlier? I meant 5,800. Which gives us a value of 5.0 times 10 to the negative 7 meters, which, remember, nanometers is times 10 to the negative 9. So this is about 500 nanometers. And you don't need to have the spectrum of light memorized, but 700 nanometers would put us, squarely in the green range. Let's actually even look it up. So colors of light and the wavelengths in nanometers. Okay. And we have these ranges, and yeah, 500 squarely in the green range, maybe a little bit blue, but yeah, we'll go with green. Which makes sense that the green is the peak of the rainbow spectrum and what our eyes evolved to be able to see, because that's the light we have here on Earth. Okay, cool. Okay, cool.